Well, let's continue. So let's see some applications of induced electric motive force or induced currents. As as I have said already, there are very diverse applications of induced currents, and one of the interesting applications is the magnetic brake. I think you have already heard about something about the magnetic brakes, and now we can discuss the magnetic brakes. So let me copy. Let's paste it here. Well, a very interesting and useful application of induced currents is the magnetic brake. So the principle of magnetic brake is shown here. It consists of the core, and around the core they're wounded coil, and this electromagnet generates the magnetic flux density B in the gap. Here it generates the magnetic flux density B, and this field is assumed to be constant. Okay, and here we can see the pendulum-like plate. In this case, the aluminum plate. It is hinged on the support so that it can move in these directions. Or if you see to the B, here shown the cross section, here shown the cross section of the situation, and this aluminum plate can move in these directions. So if the current in electromagnet I is zero, the oscillation of pendulum is not affected by the structure. Or in other words, if the current is zero, the magnetic flux density will also be zero, and our pendulum is not affected by this structure. If there is a current in the coil, the movement of conducting plate into the magnetic field generates induced current in the plate itself due to the motion of conductor in the magnetic field. So if the current I is not zero, it means some current flows in the coil and it generates some flux density. So if there is some, okay, we'll look to the picture B, to the cross section. If there is some magnetic flux density B, which is constant, and our plate is moving in this magnetic field, and because of the Faraday's law of induction, here occurs some current. In this case, here occurs eddy currents inside the plate, and the flux of induced currents is such that it opposed to the field B. Or okay, here occurs some current, and this current in turn generates another magnetic field, and the flux of this magnetic field opposes the magnetic field due to this current. And as pendulum moves on, okay, as pendulum moves on, they are generated the current, and there and inside our plate dissipated some power, and this power is or this energy is used to uh, to decrease the movement of pendulum. So now let's see some theory of this situation. So the electric field intensity due to the induced current is given as V cross B, and we get for the J, which was sigma multiplied by electric field, we get sigma V cross B. Okay, J is ampere per meter squared. And now, the velocity at which the plate goes through the gap is responsible for the magnitude of induced current. Okay, it is obvious. And the relation between current density J and magnetic flux density B and force F at some point is shown here. And okay, well, let me move this to here, and let me continue from here. Okay, force is equal to J cross B, where J was sigma V cross B cross B, and if all vectors are mutually orthogonal, okay, as in the case of our example, the total force, okay, this is force Newton per meter squared, and the total force F will be, so sigma V B squared multiplied by so V0L, okay, and its direction given by the cross product of JB. Or in other words, if we look to our figure here, its direction is to the left, which is opposite from V. Okay, is also obvious. So this has the effect of damping the movement of the plate into the gap. Okay, if the conductivity sigma of the plate was infinite, okay, if sigma was infinite, the plate would be repelled from the gap, or in if we say simply if the sigma was infinite, plate wouldn't go to the gap. Okay, next. Well, this type of electromagnetic break is commonly usually used in trains, in locomotives, or in trucks. Let's see the so let's see the scheme of that electromagnetic brake of the train. So here you can see the conducting discs are installed on the axle of vehicle, or okay, well, it is written, this is the disc and this is the side view of the mechanism. This is also disc, and it is installed on the axis of the vehicle. So this is the axis, and further in the axis there is a wheel of truck or wheel of train, and electromagnet is placed around the disc. This is the electromagnet which we have seen before. When the brakes are applied, a current will be supplied to the coil, and because of the current there occurs electric magnetic flux density B, and as disk as disk rotates in this magnetic field, inside the disk there occurs eddy currents which oppose to the movement of disk, and so uh, so the disk will start no disk will decrease its velocity. But please note that electromagnetic brake cannot be used to completely stop a vehicle. It can be used only to slow down. The magnetic brake is therefore more appropriately called the magnetic retarder or magnetic damper. So it cannot be used to completely stop the vehicle, because if the vehicle completely stops, there will not occur the induced current. That's why if there is not an induced current, there is no force opposing the movement. If there is no force, there is no the braking effect. So, well, ele electromagnetic brakes have many advantages. First, the first of all, they brake better at high speeds and are natural anti-locking brakes. Uh, okay, so let's move further. You may read from the book by yourself the other applications of uh, electromagnetic induction, such as watt-hour meter, eddy current testing of materials. Okay, experiments. Now, let's see some problems. So I have already uploaded all this material to the Moodle. You can download and read by yourself one more time. Okay, we may see a very quick summary, and after that we may move to the problems. Well, electric motive force, according to the Faraday's law, for a single loop is equal to df dphi over dt, the change of is equal to the change of magnetic flux, or for n loops, just n multiplied dphi over dt. So from these two equations for the electric field, we may write another equation for electric motive force, which is called motion action electric motive force, and is equal to the integral of from A to B V cross B dl, and the transformer action electric motive force also comes from this equation. And we have also studied the transformers. The general equation for flux inside the transformer, inside the core of transformer, is given as this. And for the ideal transformer, the ratio of electric motive force in the primary and secondary coil is equal to the ratio of number of turns of the uh, primary and secondary coils, or to the reciprocal ratio of currents in the primary and secondary coils. And the ratio of impedances is equal to the square of transformer ratio. So here the equations for the real transformer with the finite finite magnetic permeability of the core, and this is the real transformer with flux linkage in the core, where K is defined as coupling coefficient. Okay. So which problem do you want to see? Okay, first problem is not so difficult. And the next is again so multiple windings. Okay, let's see the problem number 10.19. Or 10.20, doesn't matter. Which one do you want to do? So okay, let's read the problem. Application: transformer with multiple windings. The magnetic circuit in the figure is given. Okay. Coil number one has 100 turns. This is the coil number one, and carries a current I1 equals to I0 cosine omega t. And coil number two has 50 turns and carries a current I2 equal to I0 cosine omega t, where I0 is 1 ampere and omega is 314 radians per second. The currents in the two coils are such that the magnetic flux density in the direction shown in figure. Okay. Well, magnetic flux is also given. The direction of magnetic fluxes is also given. Coil number 3 has 1000 turns. Dimensions are average lengths and are given in the figure. Okay. The cross-section area of the core is 100 centimeter per square. Relative permeability of the core is 100. Calculate V1 and V2, the voltages across terminals of coils number 1 and number 2. Calculate the induced voltage in coil number 3. Okay. How do we compute this? Hmm? Okay, do you have any idea how to start solving this problem? Perfect. No idea. Here we are given the transformer, the real transformer with finite permeability. And the electric motive force 1 in the real transformer was equal 2. L11 di1 over dt minus L12 di2 dt. And okay, this was the equation for the the for the case of transformer with 2 coils, and this is not the case for us. Now let's compute from the beginning. Total flux, the total flux inside the core is Phi1 minus Phi2, and Phi1 is so in order to find the Phi1 we need to define N1 I1 over the reluctance of the total core, and the reluctance of the total core is reluctance. So sorry, okay, let me scale down this. And similarly, Phi2 is equal to N1 I1 over the R. Sorry. So how do we compute the total reluctance of the core? So let me redraw. If you remember from the course of electrical equipment, okay, more or less, the total reluctance of the core is computed as the we divided the magnetic circuit into some parts. Okay, this is the part number 1, 2, 3, let's say 4, 5, 6, 7, 8. and, or we may do it a bit simpler, and this part is part number 1. This part is part number 2, and this part is part number 3, and here we have also air gap. And how to compute the total reluctance of the core? Total reluctance of the core is computed as reluctance first and third are in parallel, and okay, here we have one lag and one air gap which are in series. So total reluctance is equal to 1 over R1 plus 1 over R3 plus 1 over R2 plus R air gap to the power of -1. Okay, the R1 is computed as L mu S L1, let's say, R3 also computed as L3 mu S. Okay, okay, R2 also computed can be found as L2 mu S, and R reluctance of air gap is again here just mu0 because the permeability of air is mu0. So from all this, okay, we are out of time. Please reconnect quickly and we go on. I will resume. Okay, now we found reluctances R1, R2, R3, and R reluctance of air gap. Now we use superposition principle to find the. So we've found reluctances, and it means we know the flux phi1 and phi2, and using the superposition principle we can compute the flux linking the first coil and flux linking the second coil. Now let's redraw our transformer. Okay, this is Okay. So, using the superposition principle, here our second coil, here our the first coil. Okay, the flux linking the first coil we denote as phi1 prime. Flux linking the second coil we denote as phi2 prime. Using superposition principle, we want to calculate phi1 prime. Phi1 prime is equal, okay, phi1 minus phi2, let's say star. Now we want to compute phi2 star. Phi2 star is according to the voltage division rule, or yes, according to the voltage division rule, is equal to phi2 multiplied the reluctance of the second plus the reluctance of air gap over the sum of the reluctances are 1, and we can define from all this we can define phi1 prime. When we know phi1 prime, we can find the electric motive force of the first is equal as minus n1 d phi1 prime over dt. Similarly, we can find phi2 prime and then electric motive force in the second in the second coil. Okay. Okay. So Allah. Alaikum assalam. Rahmat yaxshi. Assalomu alaykum. Rahmat yaxshi. O'zingiz yaxshimisiz? Hozir 1 minut. Okay, well, similarly, we can find phi2 prime, the flux linking the second coil, which is phi2 minus phi1 star, and phi1 star can be found as okay, phi1 star can be found as using the using the voltage division rule, phi1 multiplied, so R2 plus Yep, R2 plus R delta over R2 plus R delta plus R3. And here again we can find electric motive force 2 as minus n2 the phi 2 prime over the t. Okay. Okay, you may do all the calculations by yourself and find the numeric values for electric motive force 1 and electric motive force 2. Okay.